let's move to a demo which shows the real power of the declarative way of doing things. We are going to change the properties, the configuration of our declarative pod on the fly. All that we are going to do is to make the edits that we want to our YAML template. In any case, let's pick up from where we left off. Let's list the pod. So we have two, our declarative pod as well as the imperative kubectl run command, that is the deployment object which wraps a pod within it. Let's now describe our declarative pod. Notice how we are making use of the kubectl describe command followed by the keyword pods. A whole bunch of information is displayed, and this information reflects the status of the pod. We have already discussed the difference between the specification of the pod and the status of the pod. In the Kubernetes world, there are various controllers running in the background which are constantly comparing the specification and the status and ensuring that the status, that is the actual state of the pod, reflects or most closely agrees with the specification. And that's why when we run the Kubernetes command, we get a full listing of all of the status information of our pod, starting there right up top with its status of running, that's the state, its IP address, as well as information about the containers within it. Notice, for instance, our container was started at a specific time. That was some minutes before this command was run. If we scroll down just a little bit within the same listing of status information, we can get the various events which have occurred to this pod. Notice that the first event was that our pod was scheduled. This happened when we successfully ran the kubectl -f command. The scheduler, which is a part of the control plane, kicked in and scheduled our pod. Next, a whole bunch of housekeeping stuff. Notice how on the kubelet, so this is now on a specific node in our cluster, there was a successful mount volume operation. This mount volume operation was required because the kubelet, which is running on the individual node, needed to set aside some space for the container image. We will have a lot more to say about volumes, but they are an abstraction for persistent disk or persistent storage. Once the mount had been successfully carried out, the image had to be pulled. And once again, this was done by the kubelet running on a specific node. It pulled the image nginx from Docker Hub. That pull was successful. Once that was done, our container could actually be created. Remember that our container, which runs inside the pod, comes into being as a result of interactions between the Kubernetes master plane, the kubelet, which is running on the individual pod, and the container runtime, which is also running on the individual pod. Okay, that gets us up to speed with the status of our pod. Let's now go ahead and change the underlying specification. And as we shall see, Kubernetes will update the state of our pod and pick up the changes that we've just made. So for this, we need to edit our pod YAML file. So once again, we fire up Nano, which is our favorite word editor. The API version, the kind of object which we are working with, that's the pod, none of that is really going to change. But we are going to add a label to our pod. This is going to be something under the metadata heading of the pod spec. So under metadata, we are going to specify a label, which is nothing but a key value pair. The key is going to be the word pod and the label is going to be the value updated. Nothing very fancy here. We are just tagging or marking this pod as one which we just updated. Okay, the next order of business is to apply these changes by using kubectl apply -f. And this command really is making use of the full declarative mode of Kubernetes. Because when we invoke kubectl apply -f, absolutely anything, any kind of operation might be contained within the markup which we are passing in. In this instance, our operation was to update a pod, and that's why the return value that we get is pod, declarative pod, has been configured. It's important to understand that Kubernetes was smart enough to figure out that our pod, that's the declarative pod, was already in existence. And that's why it did not seek to create a new pod called declarative pod. Rather, it merely went ahead and configured it. Let's go ahead and rerun get pods. And exactly as we expect, there are still just two pods. So we have proof that Kubernetes did not go ahead and fire up or create yet another pod. What changes? Well, if we now view the status of our declarative pod, we should see that it has been tagged with the key value pair which we specified in the YAML template. It should have that key value pair where the key is equal to pod and the value is equal to updated. Let's go ahead and run our kubectl describe pods command followed by the name of our declarative pod. And sure enough, we get a mountain of listing information from Kubernetes when we hit enter. If we carefully parse through that information, we find that there is indeed some additional metadata. Notice how there is now a status which is running, and in addition, there is a set of labels that has pod equal to updated. So the annotations which we applied from our YAML have indeed been picked up by Kubernetes. Let's try something a little more ambitious. Let's now go ahead and change the container image itself. Once again, we are going to fire up Nano, which has our declarative pod template. And within this, we are now going to change the container image. We are going to change it from Nginx to something called BusyBox. If you haven't heard of BusyBox, well, it's kind of an image with a whole bunch of little Unix or Linux applications. You can think of it as a kind of Swiss Army knife for Linux applications. So we update the image from Nginx to BusyBox. We don't change anything else. Now, this is of course a pretty major change. We are fundamentally changing the application that we are going to host within our container cluster. But Kubernetes is not phased. Once again, we just go ahead and run kubectl apply -f followed by the name of the same file. Once again, Kubernetes tells us that our pod has been configured, which indicates that it was smart enough to figure out what pod was governed by that particular application. Let's once again go ahead and get pods. This time, things are going to look a little different, and the reason for that is this major change which we have carried out on our pod is effectively going to take our pod out of action for some time. We can see that our declarative pod now shows that it is not ready and its status is set to crash loop back off, and the number of restarts of the container within that pod is equal to 2. This need not concern us too much. All that's happening in this interval is that Kubernetes is pulling the updated image, that is BusyBox, and it's going ahead and carrying out all of the underlying changes. Those changes are going to take a little while to complete, and that's why in the meantime, when we run get pods, we are going to see that our pod, that's the declarative pod, is not ready for action. But soon enough, we find that the status has changed. So it has changed to completed. This is after 3 restarts. And shortly after that, the pod is indeed in the running state. We can see from this that we can change pretty much any property of a container using the declarative mode of Kubernetes. All that we need to do is to change the pod template in the YAML, and the changes will be picked up and applied by the control plane of Kubernetes. Let's go ahead and run the describe pods command once again. This time we expect to see a large number of new events relating to our pod. So indeed, let's go ahead and run that command. Scroll down to the very bottom. Notice how the number of events is significantly greater than it previously was. The initial events are exactly those which we previously saw. For instance, the pod was scheduled, the mount volume was set up. None of that has changed. But then comes something interesting. Our container had to be killed. The container running within our pod was being changed from Nginx to BusyBox. And as a result, Kubernetes needed to kill the old Nginx container and then go ahead and bring up a new container for BusyBox. That in turn required the pod to be started, that is restarted, for various back-off states during the restart process before the image for BusyBox was successfully pulled. And once that pull had gone through successfully, Kubernetes went ahead and restarted the container and our pod was back up and ready for action.